If I tell you transformers are nothing but 14-step process, you will definitely be interested in knowing what are those 14 steps. Welcome to Unfold Data Science. My name is Aman and I am a data scientist. In this video, I will break transformer architecture into 14 steps and make it extremely simple for you. Let's start without any delay. As usual, let's try to see what all we will be covering. First of all, we will understand what are the prerequisites to understand transformers. As you know, transformer is one of the most complicated concept in AI. So there are some prerequisites which you must know, otherwise it will be very difficult for you to understand transformers. Then we will understand what are the components of transformers. Then we will go one more level down and understand what are the subcomponents of transformers. Then we will understand how the data flows in training. So suppose I want to do a language translation, how the data will flow when the training is happening in transformers. And then I'm going to show you some very interesting visualizations, some Python codes, and I'm going to discuss what will be the next steps. So this is the plan, guys. First of all, what are the prerequisites to understand transformers? Let's be very, very clear on this. Otherwise, you will get lost and it will not be easy for you to digest the concepts. Okay. So what is transformer? Basically, transformer is a combination of multiple things, right? First of all, what kind of problem transformer solves? NLP problem, right? So in NLP, what is that transformer is basically? So transformer is basically a encoder decoder architecture. Encoder decoder architecture. This is what is transformer basically. Encoder decoder kind of model. Fine. So this is one concept that you should know. What is encoder decoder kind of model? Then you should understand some basic concepts of NLP, such as what are words, what are tokens, what are embeddings, right? Then you should understand what is the meaning of positional encoding, positional encoding, because these are the things that will come as we try to understand the transformer concept. Then you should understand the basics of attention and varieties of attention, basically attention and its types. You should also understand what is the meaning of layer norm and what is the meaning of residual connection. Then you must understand what is feed forward neural network. I'm also going to give you a resource of where to learn these things. Feed forward neural network. Okay. And then since we are covering transformer, complete transformer, so two more things you should understand. One is called cross attention and another is called output generation. Output generation. Why I have listed all these things? I have listed all these things because all these things I have covered in one or other video in my current LLM playlist. Encoder decoder architecture I have covered here. So I will just show you. If you have not watched those videos, right, it's now is the point that you cannot move forward without understanding that. So I have listed down some concepts here, right? Word token embedding. If you have to understand, you must watch this understanding large language models. I have said here positional encoding. Positional encoding video I have created here if you see in the same playlist. I am saying attention and its type. If you see attention video is already there. I am saying layer norm and residual connection. So you see residual connection and layer norm video is there. I'm saying feed forward neural network. So if you see understanding large language models, I have fit a language model here and I have told what is a feed forward neural network basically. All these concepts are already there if you watch just these 5 videos. And hence I'm telling you, these 5 videos are must for you to understand transformers. And I see less interest of people in these kind of deep videos. I don't know why, but without understanding these deep videos, you will not be able to understand transformers. Simple. And then there are two concepts which I will cover today. This is basically decoder only. So In transformer, encoder does not use this concept, only decoder and the basically output. So I will say decoder only for now, decoder only concepts. So this I will cover today. Let's take a step forward now and try to understand, as I told you, after understanding prerequisites, we will go and understand component of transformer. So what is transformer at a very high level basically? Transformer is nothing but a encoder decoder architecture. So what is an encoder decoder architecture, you will ask me? So that's the architecture in the world of natural language processing where there are two components. One component is called encoder, another component is called decoder. And how the learning happens is, suppose you have a training data and the training data is basically language translation, and suppose my English sentence needs to be converted to Hindi sentence. So what is the task at hand? My English sentence, let's say, how are you is my English sentence. This needs to be converted to a Hindi sentence. For example, आप कैसे कैसे हैं. So this kind of task is called a language translation task. Taking this task as an example, right? How encoder decoder architecture will work is, you will pass your input here. So what is your input? How are you? And what encoder will do is, it will generate a context. So what it will do, it will generate a context and it will send to decoder. And what decoder will do is, it will try to generate the output आप कैसे हैं. So this is a simple encoder to decoder architecture, and transformer is also a encoder decoder architecture. At a very high level, what is this? If the task at hand is language translation, we give the input sentence and encoder encodes that, sends a context vector, decoder decodes that and generates the final output. Now transformer also is this. So let's try to put our notes as usual so that it's ready for you to download. So I will just put here, and these downloads can be done from my GitHub. What is transformer at very high level? If somebody asks you, you can simply say it's a encoder decoder architecture. And what is a encoder decoder architecture at a very high level? So I have some notes here, I will paste there. Okay. So for example, you can see this. There is an encoder. In encoder, you give your input sentence, it generates a context and gives you an output. This is transformer at high level. Now what we need to do is, we need to see what happens inside encoder and what happens inside decoder. And that is what we will do now. Before that, if you want to understand an elephant, right, you have to break the elephant into multiple components. So you cannot have a full view of the elephant standing at any one position. So what you need to do is, you need to break the elephants into piece by piece and understand what happens in encoder and what happens in decoder. Fine. And to do that, what happens in encoder and what happens in decoder, I have broken into 14 steps. So I will just put it here. I have broken what happens in encoder and what happens in decoder into 14 steps. So these are my 14 steps. So I will just put here and then we will understand. 14 steps of transformers. Fine. 14 steps of transformers. This notebook, this page will be in my GitLab. Don't worry, you can download it in GitHub. So what are the encoder steps? So let's go to the paper, the famous paper, attention is all you need. So on the left hand side, what you see here is encoder. On the right hand side, what you see here is decoder. What happens inside encoder is, as you can see, tokenization is step 0. So Step 0 is tokenization. Embedding is step 1. So I'm starting from here, embedding. Positional encoding is step 2. So I'm saying here positional encoding 2. Multi-head attention is step 3. So I'm saying step 3. Add and norm step 4. So I'm saying step 4. Feed forward neural network step 5. Step 5. Add and norm step 6. Step 6. Encoder done. Okay. So 1, 2, 3, 4, 5, 6. Now come to decoder. In decoder, shifted input plus embedding plus positional encoding, I'm saying 7. So shifted right, if you see here, it is written shifted right. So shifted right is one thing. And then embedding plus positional encoding, I'm keeping it in the same number because it's more or less same as compared to encoder. So step 7, masked self attention. Step 8, add and norm. Step 9, cross attention with encoder input. Step 10, this one. Add and norm. Step 11, this one. Feed forward 12, add and norm 13, and after this decoder block is over, right, linear and softmax I have put in one category. Final linear projection plus softmax is 14. If you understand these 14 steps, right, nobody can make you confuse in transformers, and you will never forget how transformers work. And will it not be good if I give an arrow here or a circle here and write the numbers so that when we dig deep, we can come back and understand these? And that is what I have done. So what I have done is I have I have given all the things. I have given a number, okay, and that number, what I will do, I will just put for you to understand. So all these steps. This is an image from the basic transformer architecture, like attention is all you need paper. And as I have given here numbers, right, here also I have given numbers so that when we dig deeper into the steps, right, we can come back and see which step we are talking about. Now let's take a step forward and try to understand all the steps of encoder of a transformer. So I will write here encoder steps, and then we will go into all these steps one by one. So what is step 0 basically? Step 0 is nothing but tokenization. And tokenization is a very simple concept. Most of you know what is tokens. So basically, if my input sentence is, let's say, in this scenario, my input sentence is, how are you? Then it will be basically broken into 3 tokens, and those tokens will be called how, and then are, and then you. So these will be called as tokens. So that is the reason I have put tokenization as a step 0. That is basically not something that should be given a number. I mean, it's very basic thing, right? Tokenization is 0. So I'm saying step 0 is nothing but converting your input sentence. So remember, I'm talking about training here. So this is converting your input sentence to tokens. This is your step 0. What is step 1? Step 1, if you come here and see, right, step 1 is embedding, and step 2 is positional encoding. So if you come to the architecture, right, step 1 is input embeddings. So here how many words I have? 1, 2, and 3. So how many embeddings I will have? 3 embeddings. In those 3 embeddings, my positional encoding vector will come and get added, right? So somebody who has watched my previous videos on residual connection, positional encoding, right, they will be very easily able to correlate. So what is happening here? Embeddings will come, positional encoding will get added to the embedding. That's it. Step 1 and step 2. Embeddings will come, positional encoding will get added to the embedding. So I will write here step 1 and step 2. What are step 1 and step 2? If I have to represent in a picture, right, what I can do is I can simply represent it like something like this. So I have an image for all the things so that it will be very easy for you to understand. How many words we have? How are you? What is the first thing that will happen? Embedding will get generated. What is the second thing that will happen? Positional encoding will come and get added to the embedding. So this plus I'm talking about. These two things added, and then first and second is done. Then it will enter to the attention layer, which we will see next. embedding plus positional encoding. I am saying enhanced embedding 1, enhanced embedding 2, enhanced embedding 3. So for 3 words, how are you? Now we have got enhanced embedding 1, 2 and 3. So step 1 and 2 of transformers encoder is done. Now let's go ahead and see what happens in step 3 and 4. Step 3 and 4. What happens in step 3 and 4? Step 3 and 4 is basically, if you come here, multi-head attention and add and norm. So what will happen? Whatever is the output entering, that will go to multi-head attention, and it will also go to residual connection, and finally the layer normalized output will come out. This also I have shown in detail in the video of residual connection and layer normalization. So people who have watched that, it will be very easy for them again. And if I have to draw that, what will happen in this, right? What I can do is I can paste on that screenshot there for you to download. And step 3 and 4 can be represented as this. So what you can see here, the embedding that has come from above, the enhanced embedding 1, enhanced embedding 2, enhanced embedding 3, is going to a multi-head attention layer. So see the diagram here, multi-head attention layer, that is step 3. And then the output of attention will get added to the original thing through a residual connection. So that is what is happening here. Attention output 1, attention output 2, attention output 3 is getting added to the original enhanced embedding. And both these sum is passing through a layer normalization, and we are getting layer normalization 1 output, layer normalization 2, layer normalization 3. So our step 3 and step 4 is done. So we are here now. Okay, we are here. And then we need to move to step 5 and step 6. So what is step 5 and step 6? Basically a feed forward neural network and again add and norm. So I will write here step 5 and step 6. Step 5 and step 6. What is step 5 and step 6? If I have to represent that in a picture again. So step 5 and step 6 also will be basically your whatever is the output from previous layer will go to a feed forward neural network, and then from there, so output from previous layer is what? ln1, ln2, ln3, right? So ln1, ln2, ln3 is going to a feed forward layer, and then feed forward 1 output comes, feed forward 2 output comes, feed forward 3 output comes, and the original ln1, ln2, ln3 gets added. Why? Because of layer normalization. So let me show you from here, otherwise a lot of times I need to scroll. So I'm here, right? This is the output from step 3 and 4 here. This output goes to feed forward, okay? And the same output goes to residual connection as well. So what will happen? Feed forward output will come, residual connection will get added, and then normalized. That's exactly what is happening. Feed forward output will come, previous layers thing will get added, and then layer normalization will happen. Now one important thing here is whatever you have done till here needs to be done 6 times. So as you can see here, in the original paper they are saying nx. Nx means in transformer architecture there is not only one encoder, rather there are set of encoders. Okay, and set of encoders means how many encoders? 6 encoders. So output of one will enter to next, and output of next will enter to next. Basically the first encoder's output will be input to the next encoder, and so on and so forth till 6 times. That is the reason I'm saying here to be repeated 6 times. To be repeated 6 times. Why? Because this nx is 6 encoders. So same process will repeat 6 times. Obviously the network will be different. Feed forward, attention, weights, all these things will be different. But the architecture wise it will be same. Okay. 6 encoder it will come, and finally what you are going to get after 6 times is encoder output 1, encoder output 2, encoder output 3. Remember this? Encoder, how many steps we are covering? 6 steps. Tokenization, embedding, positional encoding, multi-attention, add and norm, feed forward, add and norm again. That is what we have done here. Okay. Finally, what you will have, encoder first tokens output, encoder second tokens output, encoder third tokens output. And this is what will go to the decoder now. So if you go here, right, you see here encoder thing is entering into decoder, right? So you need to understand what is the final encoder output. That is what I am saying here. After 6 encoders, you will get encoder output 1, encoder output 2, encoder output 3. Basically the tokens embedding I am talking about, contextual embeddings. And then it will enter to the decoder. How? Let's see now. If you have understood till here, then please don't forget to write a comment, because if your comments don't come, the message I get is my work is not reaching you. Okay, so if you find this useful, please drop a comment saying I'm understanding and this is good, or whatever you feel. So we have done the encoder steps. Now we will understand decoder steps. And in our definition of steps, right, how many steps we have put in decoder? We have put 7 steps here. Up to 6 is encoder, and then next 8, 1, 2, 3, 4, 5, 6, 7, 8. Next 8 things are happening inside decoder. So inside decoder, if you go right, you will see that it is saying output shifted right. I want you to understand what is the meaning of output shifted right. So let me try to explain you in my note here. What is the meaning of output shifted right? So when the training is happening, right, encoder will be given this input and decoder will be given this input. Decoder need to understand where is sentence starting. So if you give decoder आप कैसे हैं, what decoder will do is it will add an additional start token. So start of sentence it will say, and then it will compute these tokens. आप कैसे हैं. So basically what is happening here is your output is shifting right, because SOS is one more token added, right? So actually here is 3 tokens only, but what decoder is working on will be in the actual input 3 tokens, but decoder will work on 4 tokens. Sometimes it also gives a end of sentence, so maybe it will work on 5 tokens also. For simplicity, let's take 4 tokens, and this SOS is what is an additional token. This process is called shifting right. That is what is written here, shifting right. Okay, and then the usual suspect, right? So embedding will go and positional encoding will come. Both these together I am calling as step 7. Fine. So in encoder, I was calling 2 different steps to make you understand. Here I am calling both these together as step 7. If I have to draw step 7, how it will be? If I have to draw step 7, how it will be? You can visualize, right? So basically shift right will come into picture, and we can put the values here. So for example, आप कैसे हैं will be the input. Shift right will come, then start of sentence will come, then one place shifting right will come, embeddings will come, positional encoding will get added, right? And then decoder embedding 1, decoder embedding 2, decoder embedding 3, decoder embedding 4 will come. So basically what we are doing, we are here, we have shifted the output right, and then embeddings, and then positional encoding. What goes inside encoder block is basically decoder embedding 1, decoder embedding 2, embedding 3, embedding 4. So this is basically which step. Let's put here step 7. Step 7. Now we will do step 8. And what is the step 8 here? Step 8 is basically masked multi-head attention. In our drawing, what is step 8? Let's try to see once. In our drawing, step 8 is masked multi-head attention, and step 9 is add and norm. So what will happen here? Basically, whatever is coming inside the decoder, that will go in masked multi-head attention. Again, masked multi-attention I have explained you here in multi-attention video. Those who have watched, it will be easy for them. Those who have not watched, please go and watch. Masked multi-attention will come and add and norm will work. So it's very similar to how encoder attention is working. A simple difference here, masked attention is working. That's it. In encoder, there was no masked attention, and here masked attention is working. Now you have to comment me why decoder uses masked attention. That is your homework. I'm pasting this. Meanwhile, you can comment why decoder uses masked attention. What is the need of using masked attention? So as I was telling you, after step 7, right, there has to be a step 8 and 9. That is this step 8 and 9. And what 8 and 9 does? Decoder embedding will come. It will enter masked multi-attention. Masked attention output 1, masked attention output 2, 3, 4. And then decoder original embedding will come because residual connection need to work. Plus will happen. It will go to layered norm as usual. And then layered norm output 1, layered norm output 2, layered norm output 3, layered norm output 4 will come. So step 8 and step 9 is done. So if we have to see here, right, step 10 and step 9, this part is done. Now we want to go here. So one interesting thing happening here is, if you can see, right, encoder output is coming and entering in this multi-head attention. And this output is also going into multi-head attention. I will repeat it again. Whatever you are getting from input is entering in multi-head attention, and whatever you are carrying till now in decoder is also entering multi-head attention. What is the meaning? The meaning is it's a cross attention scenario. What is the meaning of cross attention? Very simple. Attention, if you understand, you will know what is query key and value from this video. In attention, you will take query from decoder and key and value from encoder. That's it. That's your cross attention. And this is your cross attention layer. Okay. And after this cross attention, add and norm will come as usual. So please remember, people will ask you in interview where cross attention is used in transformers. Remember this step. Step number 10. So here you use cross attention. Query you take from below and key and value you take from here, and then add and norm work as usual. So if I have to represent step 10 and step 11, how can I represent that? So let me write here step 10 and 11. If I have to represent step 10 and 11, how can I represent? I can simply, by some way, I have to say that it is a cross attention encoder output is coming here. And that is what I'm going to do through this image. So if you see this image, right, layer norm 01, 02, 03, 04 will come obviously. And then EN01, 02, 03 is coming. So where from this EN01, 02, 03 is coming? I told you this is encoder output. EN01, 02, 03, same color, okay? EN01, EN02, EN03. And here LN01 is coming from previous layer of decoder. EN01 is coming from encoder. And hence I'm calling here cross attention. Cross attention Q decoder, KV encoder. Very simple. Query will come from decoder and K and V will come from encoder. And what you are going to get an output is cross attention output 1, cross attention output 2, cross attention output 3, cross attention output 4. As usual, you combine with previous layer norm output, previous layers output basically, and residual connection as usual, pass it through layer norm and you get layer norm 1, 1, layer norm 1, 2, layer norm 1, 3, layer norm 1, 4. So I'm calling this layer norm 1, 1, 1, 2, 1, 1, 3, 1, 4. So basically I have reached here. And then what I need to do? I need to just pass it through one feed forward and add a norm. And what I'm calling in my numbering there, in my numbering, what I'm calling feed forward, I'm calling 12, and add a norm, I'm calling 13. So Let me write here step 12 and step 13. I hope you are enjoying this video, guys. If you are enjoying, don't hesitate to press like, please. It takes a lot of effort to create this kind of content, guys. You can see the hard work here, okay? Hours and hours of hard work is here. It's not something that is taken from somewhere, that is copied from somewhere. It's everything I need to write myself. I need to create, okay? If you feel it is worth your comment and likes, please don't, you know, uh, hesitate to do that. So step 12 and step 13, what is that basically? Step 12 and step 13 is a simple layer norm output will come and it will go to the feed forward layer. And once it goes to the feed forward layer, then what we are going to get an output, feed forward layer output 1, feed forward layer output 2. See here, feed forward 1, feed forward 2, feed forward 3, feed forward 4. Get added to layer norm 1, 1, layer norm 1, 2, layer norm 1, 3, layer norm 1, 4. Go to layer normalization and then layer norm 2, 1, layer norm 2, 2, layer norm 2, 3, layer norm 2, 4. And I am writing here to be repeated 6 times. Now you know what I mean when I say this. Decoder also is nx, and in original transformer this x is 6. Fine. So 6 times this will also repeat this box. So just like encoder, decoder also will repeat 6 times and then you will have the output. What will be your final output when you do it 6 times? When you do it 6 times, right? You will have 4 embeddings, basically 4 enhanced embeddings to call it. Now there is something very interesting. After you have those embeddings, then what you do to generate the output? So I will explain you in note that part is really interesting. After your decoder has run, right? So you will have 4 enhanced embedding for 4 tokens. Up. How many tokens you are processing in decoder? 4. What you will have? 4 enhanced embeddings. So this is, let's say, in my explanation, what I am calling as here, what I am calling as ln21, ln22, ln23, ln24. Okay, so layer norm 21 to 22, let's say layer norm 21, ln22, ln23, and ln24. So what you are having is 4 embeddings basically. What are these embeddings? These are basically context aware embeddings. So these are basically very much context aware embeddings. Now the thing is, how do you make the prediction? Fine. So this is your actual training data, right? So this is, you can think of this as your training data, and your model is training. When your model is training, it is trying to predict these tokens, and in the final step it has ended with 4 contextual embeddings. Fine. Using these embeddings, if the model is 100% correct, it should predict these tokens. Okay. So how it will work in the final layer, step 14, is we have to understand few details here. First of all, what is the size of this metric that I am talking about here? Size of one vector will be equal to what is your embedding size. Suppose your embedding size is 512. So all these vectors will be 512 dimensions, correct? All these vectors will be 512 dimension if your embedding dimension is 512. So size of each vector is 512. And if you stack that together, right, what will be the size of matrix? 4 rows for 4 contextual vector into 512. This is your size of matrix. So what you are going to get output from here is a matrix of 4 into 512. Correct? Now let us assume that your vocab size Vocab size means what is the total number of words in your output vocabulary. So assume size of vocab is 10k. Just an example I am giving. Assume size of vocab is equal to 10,000. At the moment I say 10,000 is size of my vocabulary, that means that all these embeddings can predict any of these 10,000 words. They are free to predict any of these 10,000 words because that is the size of my vocab. So what I need to do is I need to somehow create a process that will help me bringing probability number of which word out of that 10,000 tokens is my prediction. Fine. And to do that, I'll use a linear layer. So here you see a linear layer, right? Linear layer is nothing but it's a again trainable weights. Okay, so imagine there is a weight matrix. And weight matrix size is 10,000 into 512. So imagine there is a weight matrix. And weight matrix size is basically how much? 10,000, because 10,000 is vocab size, multiplied by 512 is the embedding dimension. Fine. And then there will be a bias metric as well. You can think of these as learnable parameters. Don't worry much about this. Bias matrix size is also 10,000. 10,000 numbers, basically 10,000 biases. Now what you will do is you will run a function called logit. So what is the function that you will run? And that logit will be basically x multiplied by w transpose plus b. B is for bias. And in terms of size, your x metric is of size 4 into 512, and your w transpose metric will be of size, if you flip it, right, 512 into 10k, 512 into 10,000, and then there will be b. Don't worry about b. The final matrix size that you are going to get will be 4 into 10,000. The meaning of this is you will have a big matrix here. You will have a big matrix here with 4 rows and 10,000 numbers. How many numbers? 10,000 numbers. And how many rows? 4 rows. 1, 2, 3 and 4. And in all these you will have 10,000 numbers. Starting from this, the size will be 10,000. This will be 4 into 10,000. 4 into 10,000. This process that you have done till now, right? This process is called linear layer, or applying linear transformation, or that linear layer or linear function is written in the architecture right here. This process is called linear. Once you pass through linear, right, for all the tokens, you started from here, right? You have some ln21, ln22, ln23, ln24, right? For all these 4 things, right, you will have 10,000 numbers in front of you. ln21, ln22, ln23 and ln24. This is your second last step, but this is still not probabilities. These are linear projections, so that you just have 10,000 numbers, but you need to convert it to probability so that you can predict which token this ln21 represents, which token ln22 represents, which token ln23 represents, and which token ln24 represents. How you will do that? You need to convert this 10,000 size vector to you need to convert this 10,000 vector to a 10,000 number probability and you need to pick the highest probability. I will show you in Python also now, don't worry. If you apply if you apply softmax on this, right? If you apply softmax on this, what you are going to get is 10,000 probabilities here. How many probabilities? 10,000 probabilities for all the tokens. And whichever is the highest probability, right? That is the prediction for that particular token. So how many numbers you have in front of you? 10,000 numbers. Fine. Whichever number is highest, because these are probability numbers, whichever number is highest, that corresponding token becomes prediction for ln21, and so on and so forth for these. And this process is softmax process, the last process in the here. Softmax, then output probabilities. Linear, then softmax. What is happening in linear? Nothing much. A weight matrix is there, bias matrix is there. We are projecting it to a 10K dimension space. And then we apply softmax to get the probabilities. Fine. And if I have to give you a diagram which you can refer to, I have that for you. Let me give it to you. And this is what? This is basically step 14. Step 14. And I will paste it here. So ln21, ln22, ln23, ln24 you have. You take ln21, 22, 23, 24. Context aware vectors you take. Size of matrix is 4 into 12 basically x. Assume output vocab size 10K. Weight matrix shape 10K into 512. Bias matrix shape 10K. Logit xwt plus b. Result matrix size 4 into 10,000 linear layer. Apply softmax to get probability softmax layer, and whichever probability is higher, right? Highest basically. I'm saying Maxwell predicted token. Now let me show you this in Python. Import torch.nn import torch functional. Simulate decoder output for a token. For one token, right? Let us assume that for one token, this is decoder output. So let's say this is your decoder output for one token. This is a dummy output basically. So what will be the size? Size will be 512. Okay, so 512 vector you have here. And as I told you, you will start from 512 vector. So imagine that for ln21, I have a 512 size vector. So weight matrix and bias matrix should be defined here. That is what is happening here when you define the linear layer, right? You are saying 512 into 10K. D model 512, vocab size 10K. So you're doing this. Then pass through linear layer, get logits. This is unnormalized score basically. Passing through logits, so you will have 10,000 numbers, but you will not have the probabilities which you can see and you can get the output. So these are basically unnormalized score and 10,000 dimension score basically. And to get the probability, you simply have to pass it through softmax and use argmax to get predicted token ID. So what I'm doing, I'm going to props and I'm taking the argmax, whichever is the highest, that is my predicted token. So predicted token ID is basically 8627. So whatever token number is 8627 is prediction in this case. So I explained you the last two steps, sorry, last one step, but two basically sub parts of that: linear layer and softmax layer. And this way, what will happen? What will happen is you will see in the end, it will say for these four tokens, ideally it should be predicting आप कैसे हैं. Okay, so you will not see SOS when the prediction happens. You'll only see आप कैसे हैं. So that is how you can divide transformer into, first of all, encoder and decoder. You can divide encoder into 6 steps, decoder into 8 steps. You can number it and you can see what happens. Step 0, step 1, 2, 3, 4, 5, 6, 7, 8, 7, 7, 8, 9, 10, 11, 12 and 13 and 14. 14 is something which may need some of your more attention, But it's simple. I mean, it's not a thing that you will not understand. Basically, a game of weight and bias is here to project it in a new dimension, and then softmax to get the probabilities, and whichever is highest probability, that token will be selected. So after a lot of efforts, guys, after lot of hours spending, I'm able to explain you transformer is in a very simple way that I think you will be always able to remember, because you will not forget this. Okay, download this from my GitHub, and keep it with you, and you can refer it anytime. And if you are liking the videos in this series, guys, please don't forget to like, share with your friends so that I get more motivation to create similar content. Fine. See you all with another interesting video. Till then, wherever you are, stay safe and take care.